In this lecture, we'll be taking a closer look at the external processes which are responsible for landform development and change. We will take a closer look at what happens after a landscape is, in a sense, initially shaped through tectonic processes. In this case, we will take a closer look at things like denudation or erosion. We will look at mass movement, and we will attempt to understand something about how a landscape changes systematically. Let's begin by taking a look at some basic terms and ideas. Our understanding of earthly landforms must not be a vacuumous one. As is the case with all geosystems, physical landforms interact and interrelate with all of the earthly systems that we study in the curriculum of this course. We must then familiarize ourselves with landform development. This concept is important and is carried through a good portion of the course. As was the case with the ideal notion of the landform slope, we will see landforms, their genesis and change, to be an important central theme in the third portion of the course. Today we'll familiarize ourselves with the basics of landform analysis as a science in physical geographic pursuits. Let's take a closer look too at what has developed as its own specialization with regard to this topic, which in this case is geomorphology. Geomorphology is the science of landforms. Geomorphologists study their origin, their evolution, their form and spatial distribution across the Earth's lithosphere, and of course they tie all of these concepts into the many different processes that are at work within the earthly system. Geomorphology is a science that really is an important aspect of the broader discipline of physical geography. One key process that geomorphologists will initially study falls under the term denudation. Denudation in this case is any process that wears away or rearranges landforms and the particles that compose them. This body of processes includes things like weathering, mass movement, which we talked about in a previous lecture, erosion, the transportation of particles, and the deposition of particles. If you have a chance to compare some of what we are talking in this lecture to the opening slide in our look at water and weathering, you will start to see a connection between some of the terminology and the idea of slope. Additionally, you will be able to identify where these particular agents of erosion exist. The agents involved in these processes are as follows. We have air, we have water, we have wind, we have ice, and then we have the probably most important source of energy, even though there is an additional source that we'll talk about, but right now we'll look at another agent known as gravity. The interaction between the structural elements of the lithosphere or any landscape within it and these agents of change is very, very complex. However, geomorphologists attempt to understand these interactions mathematically, and they attempt to predict where a landscape may be going. These agents, in a sense, are in a continuing struggle or constant struggle. They also represent a continuing struggle between the Earth's internal and external systematic processes, between the physical character of earthly materials and the weathering and erosion as processes that are at work to change them. For example, what is known as the Delicate Arch of Utah, a 15-story weathered stone arch, physically depicts the struggle between earthly materials and the processes of weathering and erosion. In its structure, we see the differing resistance of lithic material coupled with variations in the processes that attempt to break down the sedimentary stone. In this case, it becomes an excellent example, or we're given an excellent example, of differential weathering in the sculpting of the landform itself. Different layers of the landform, different layers of composition having to do with the landform and the landscape that surrounds it will weather at different rates. Also in this case, endogenic processes, in a sense, build an initial landscape, and exogenic processes develop a sequential landscape that we see in the body of the arch itself. This means that in the material makeup of the original sediments, the original lithified sedimentary rock, we have an initial landscape that is a byproduct of endogenic processes. Then, when we juxtapose that with what we have today in this 15-story weathered arch, we are looking at an exogenic development, or a landscape that has gone through a series of developmental stages. So in a sense, it becomes a kind of sequential landscape that the geomorphologist can then pick apart and understand with regard to the evolution of landscapes within this region, this Four Corners region of the American Southwest. Well, where do these ideas come from? Let's take a closer look at that. William Morris Davis, born in 1850, becomes a very important individual when we start to look at how geomorphologists study landform development. He first codified what is today termed the erosional cycle or rather the geomorphic cycle model. Davis theorized that a landscape undergoes an initial stage of uplift that is accompanied by erosion, or the removal of materials. The uplift, in Davis's perspective, and this is something that is still agreed upon today, directly connects that landscape to tectonic processes. He also believed, and it is something that has been verified through scientific research over time, that the uplifted landscape is then broken down generally by the workings of water. Streams begin flowing, cutting rapidly into a landscape, weathering it, eroding it. And when these initial flows, surface flows of water, begin to change a landscape, they will express very high levels of energy. They will be able to rapidly weather something, lift those particles up in their own load, and carry those to areas of lower energy output. Davis believed that the energy expression in this process of having water particles break down a landscape or transform a landscape into something that we see today was most greatly expressed in terms of the energy in the headward or upward stream environment. He believed that, and this is something that we have been able to verify mathematically, that stream actions closer to the point of origin, or to a point of origin in a headward environment, are going to run in a more linear fashion and more deeply. Davis also believed that the slope angle of a landscape, if we were to take that landscape and kind of cut it like a cake down the middle and look at it in profile view, and look specifically at the angles that the work of water are producing, the slope angle or angles in a landscape is or are gradually reducing over time as ridges and divides that initially develop in a landscape become more rounded and their elevations become lower. According to Davis's cyclical model, the landscape eventually evolves into an old erosional surface. An old erosional surface. So this was kind of the conclusion to Davis's model. The idea that a lot of what we see today in the modern world is really ancient. Today, most geomorphologists prefer the expression dynamic equilibrium model with regard to what Davis explained. This model emphasizes the balance between force, form, and process. The balance between these three constructs will be our focus as we discuss landform dynamics over the remaining weeks of our lecture. This model, adopted by geomorphologists really in the late 1960s, focuses on the interplay between tectonic uplift or crustal plates and their work, and the wear or the erosion and weathering processes that are continually at work on these plates. Let me give you a couple more definitions. First, weathering. Weathering is the process by which surface and subsurface rock disintegrates or dissolves or is physically broken down. Rocks at or near the Earth's surface are exposed to physical and chemical types of weathering. Rock, as we have mentioned earlier, and in this case, is an assemblage of minerals that are bound together. Erosion is denudation by wind, water, or ice, which dislodges or dissolves or removes surface materials. As you can see, these terms are conceptually very close to one another. In fact, they probably overlap. However, erosion is a more general term and can be applied to both natural and cultural landform features. So, a landscape is an open system. Uplift, in this case, creates the energy potential for a landform system. Uplift, as I mentioned before, relates to tectonic activity. Endogenic or internal processes result in the gradual uplift of new landforms. The best example of uplift occurs along plate boundaries, or where we find many of our mountains, mountain chains, and processes of mountain building. Potential energy in this case is the presence of lithospheric materials above or being pushed close to sea level. So once tectonic uplift pushes material at or above sea level, and of course it can be significantly pushed above sea level in terms of overall elevation or distance. Once that is set, now we have an energy potential for a landscape. And uplift is the cause or the source of this energy potential. Then, endogenic events such as earthquakes and volcanic eruptions, or exogenic events such as heavy rainfall or a forest fire, provide new relationships for the landscape to be modified by. Most of these events will interact with that initial energy potential that is established by uplift. So, just to review, we have uplift in this model, creating the energy potential in the landscape, followed by endogenic and exogenic processes which begin to break it down, some of which, again, act upon that potential. Then the last stage is destabilization events. So endogenic and exogenic processes are then followed by destabilization events, in which landform systems are attempting to reach a geomorphic threshold. A geomorphic threshold is the point at which there is enough energy within the system to overcome material resistance, or the resistance material has to movement. In a sense, landscapes are always trying to rebalance themselves. Let's take a look at an image that we looked at previously when we were talking about the mass movement of material and its relationship with water, in this case when a landscape becomes saturated. The depicted slope in this case is in a state of disequilibrium. Another way of looking at it mathematically is that this almost collapsed slope is in a sense in a state of compensating adjustment. The failure of saturated slopes to remain intact led to the rapid movement of a section of the land surface, causing in this case a landslide into the river and the establishment of a disequilibrium in the slope. As a result, a dam of material threw the associated stream into its own disequilibrium with regard to things like flow and the movement of sediments or sedimentary load. So in a sense, we have in this one picture a few different events going on. We have the soil moisture levels increasing to the point at which they can no longer remain intact. As a result, the entire landscape, or at least a portion of this landscape, and this is part of its evolution, is going to move rapidly. We will have a sudden downward slope movement of material, including the plants, maybe even some of the animals that are living in this region. Once this occurs, once we have water, particles, and of course elevation all interacting with one another in the kind of soil landscape, and we have this mass movement of material into a stream body, now we are having one landscape impact another. What I mean by that is all of this material, including some of the plant material that is being kind of washed down from a higher elevation, is moving from an area of very high energy to very low energy. And as it's doing so, it is impacting another natural system, in this case, a watershed. This concept brings us to our last two terms as we begin to look at how weathering and erosion function within a landscape and the history of a landscape. These terms relate to stream action, an important mechanism in both the process of weathering and erosion, and of course an important mechanism to understand how landforms are developing or where they might be in their kind of constant process of change. The terms that we will associate in this case are, first of all, flow. Flow can relate to the mass movement of land surfaces, but generally it will relate to stream action. Flow in this case relates to the discharge associated with the surface runoff of water. The type of flow associated with moving water will define the nature of its transport or even what it transports. We have another related term, in this case, laminar flow. Laminar flow, for example, is a streamlined flow pattern in which individual particles, things like clay or sand, or any really fine particles, move evenly along generally parallel paths. Laminar flow is associated with streams of water that have depth to them and where channel surfaces are relatively smooth. Our other term, load, in this case, relates to the moving water. So the load of moving water, surface or subsurface water, is the material that it is carried or that it is carrying. We recognize two types of load. First, dissolved load or load in solution. The material remains, in this case, derived from the denudation of minerals or mineral compounds. Examples of parent resources for this kind of load would be things like limestone, dolomite, or any sort of soluble salts. The other kind of load would be suspended load. This one is something that I think we all can relate to a little more easily. Suspended load consists of the fine-grained clastic particles, things like sand, that are held aloft within water flow and remain a physical part of the flow until water velocities decrease to a point where the load that they can potentially carry is diminished. So suspended load, again, consists of fine-grained particles held aloft within flow until that flow no longer has the energy to hold them aloft and begins to deposit them. The concepts of flow and load then become important with regard to weathering and erosion when we're talking about how material is moving through a landscape. Realize also that flow and load will interact with areas of high energy where things are being eroded and initially kind of broken down or moved. And they can also interact with things, particles within a landscape in areas of low energy where we are starting to see things deposited or particles deposited as new elements of that landscape begin to develop or as the landscape's elevations begin to, in a sense, even out. So in a sense, flow and load become very important concepts as we attempt to mathematically understand how a landscape is changing, how particles might be moving through that landscape, even when we can't recognize them with our naked eye. The idea of the development of a sinkhole when we're talking about a karst topography. This can be something that's going on that we have little to no understanding of as we stand on the terrestrial surface until suddenly we have this mass movement of material as things attempt to compensate themselves within the landscape, and we have the development of a sinkhole. Your author will address stream concepts, stream geomorphological concepts, rather extensively. Please cross-reference that material from your readings to what we were looking at in the latter portions of this lecture.